second. Preparing to live stream the meeting.
Is it just the presenter that shows up on YouTube, or are all of our faces there too?
Everyone.
Okay.
Are you? Yeah. If you guys don't want to show up, you should yeah, turn yourself off. Are you good with recording and everything, Rob?
Sure.
All right. Okay, so I'm turning on recording. And we are live with one more PurPL seminar. Today, we have Rob Dickerson presenting on, oh my God, I forgot the name of your dog.
Yeah, me too. It's relational reasoning with specifications.
So there you go. So Rob has extensive experience on the industry, and he's a third-year PhD student under Ben Delaware. And he has worked on Riot and Square, which are pretty cool companies, and he has extensive engineering experience, which I always really appreciate in our meetings. So with you guys, Rob Dickerson, thank you.
Thanks. All right, so I need to learn how to share my screen in Zoom.
Oh, I believe I have to give you the permission first.
Okay, that's maybe why I can't see it.
So you're good.
Okay.
There should be a big green button you should just click.
Host disabled participant screen sharing is what I see. Oh, there's a different button. Yeah, it still says host disabled participant screen sharing.
Again.
Okay.
I've changed it.
Okay.
Try that. Does it work now? Aha.
Can you see this?
Perfect.
Okay, let me see if I can full screen this real quick. Do I have to like stop sharing to interact with the window? That's fun.
Okay, I think the thing you can move around, so you can put it somewhere that doesn't stay in front of you.
Gotcha. The keyboard shortcut isn't working. There we go. Can everyone see this? There's still a title bar, it's fine.
Yeah, there's, can you move things around so we can double check?
Yeah, trying to advance the slides.
Good.
Yep.
Okay,
right. Great. Yeah.
Cool.
Yours.
Okay. So like Pedro said, I'm going to be talking about relational reasoning with specifications. So this is ongoing work that we've been doing. I've been doing this work along with Ben Delaware, my advisor, and Shenchuan's helped out too. And yeah, this is hopefully it is. I'm going to be optimistic and say it's on the cusp of getting published, but we'll see, I guess. So to start out, I want to talk about a concept that I think probably everyone here is familiar with, which is modular code design. So what do I mean when I say modular code? I just mean that, okay. That we want to separate our programs into these sort of standalone parts that we can switch in and out. So a common example would be like an API that you call, and you can switch it out for other APIs or whatever. I'm sure everyone's familiar with the idea. We use it all the time. Here's a simple Python program that grabs data from some URL and saves it to disk. So when we write code like this, we're using pieces of functionality that we don't really know what they do. We just trust that they're going to perform some job. So here's a list of things that we don't have to care about when we write this code. When we invoke requests, it's using some network protocol in the back end. We don't care what that is as long as it does what it's supposed to, which is give us the data. When we hit this endpoint on the server, we don't really care what the server stack is. Is it like LAMP? Or is it like some microservice thing? Doesn't matter as long as it does its job and returns the data we want. When we write to the file, open the file, write to the file, Python runtime is making these calls to the operating system, which in turn may calls to like some file system, and we don't really care about the details of that. And in fact, we might run this program in different environments where the details of that get swapped in and out. But we don't care. All we care is that it meets its spec, that it does what it's supposed to, right? So unsurprisingly, this is good, right? Because it means that we don't have to care about things. We hide this implementation behind this specification. So that when we write our code, we don't have to think about all the details of these implementations. All we have to do is think about the specification, what job the thing does, right? But this sort of modular code can present a challenge when we're reasoning about program logic. So program logics here, logics that step through code line by line to reason about them, right? Why is this can be a challenge? Well, the same reason. It hides implementation behind the specification. So when we're trying to reason about a program by looking at it line by line and thinking about what the transformations are, like logical transforms are for each like line of syntax, all of a sudden we'll hit this gap where we know there's a specification, but we don't know what the actual implementation does. So to kind of give an example of this kind of thing, I want to look at just a simple example of a refactoring. So here we have some Java code that computes the median of an array of integers. So it's kind of, let's be honest, kind of a mess. Like if you wanted to figure out what this does, you would have to sort of like look at it for a while and figure out what's going on here. But what's going on here is that this highlighted section here from lines 2 to 11, this is sorting the array, and it's doing it via an insertion sort. And the rest of the function is doing sort of the interesting bit or whatever, what median is, which is it's getting the middle element of the array once it's been sorted. Technically, when you do median, you're supposed to average the middle two numbers if it's an even number of things. We're not going to worry about that. We're just going to take the midpoint and one below the midpoint, I guess, if it's an even number of things. So what refactoring might we want to do here? We might want to pull out this messy bit of code that's doing the sort, and because we don't really care about that as much. All we care about is that the sort happens, right? So we move sort into its own method. We don't really care about it as long as it does its job. And since we're talking about specifications and programs that we don't care about what they do as long as they do their job, we'll go ahead and assume that we can use any sort here as long as it meets some specification. And obviously specifications in the real world are often not given formally, but we're talking about formal reasoning. So we'll assume we have some formal specification, and here's what it is. Specification is going to have the form of a pre and post condition. So the precondition here is true, which means we can call sort any program state we want. And the post condition will be that the array, any index into the array, if the index is if the index I is less than or equal to the index j, then the value at the array at those indices should also be, the value should be less than or equal to the value at j. And then we also have this other condition that so by this array subset of permutation, here I mean permutation to be the set of permutations of the original array. And we can't add or remove elements from the array. Okay, so now we've done this refactoring. We want to verify that we've done it correctly, let's say, because that's an interesting thing to do. So what do? We have this thing on the left, which I'll call P1, which is our first program. And then we have this thing on the right, which are the changes that we made to the program. We sort of pulled out this sort, and then we hid it behind a specification. So this program sort of contains some code as well as a spec. Doing this kind of verification where we care about the execution of two different programs. This is going to correspond to verifying a relational property. So here we have, okay. So here we have a relational precondition and a relational postcondition. So you can read the subscripts here as being talking about the value of this like array. Subscript 1 is the value of array in the first program on P1. That's the left-hand side. So what makes this relational? Well, we're talking about the execution of two different programs. We're relating the two programs together when the states meet these conditions that can talk about states in the multiple executions. So what are we going to say? When are we going to say our refactoring is correct? Well, it's correct whenever we start out with the same array, we end up with the same return value. So this is a simple notion of correctness. It's just saying that we always get the same return value, right? And how would we do the verification? Actually prove that this property is true. There's existing work usually in the space of relational Hoare logics. I'm going to step through a couple steps of how a proof might look here, but if you don't really care, feel free to like zone out until we're done with this, but just to kind of show how it works, remember we have these P1, P2, and these are the two different programs. So we have this triple, the thing in brackets on the left-hand side is our precondition, the relational precondition, brackets on the right-hand side is the relational postcondition. This little tilde is just a little delimiter between the programs. And you know, if we want to actually go through the proof, we would sort of say, okay, P2 ends with this return array. I'm using the overbar instead of the array, you know, it's the mid value of the array, the middle value of the array, just to save space. But anyway, so the last line of our program was to return the midpoint of this array. So we're going to use some like weakest precondition to modify the postcondition of our triple, and we can sort of like start stepping through the code. You know, there are multiple strategies out here for doing this, and you can construct elaborate product programs, or whatever. But we're just going to start stepping through the last lines of the code here, and we can do this until we get to this sort. So what do we do with sort? This is sort of the place where we might get stuck because we don't actually have an implementation for sort on the right-hand side. All we have is a specification. So we're going to need a rule to handle specifications in a single execution context, which we can do. So here's a rule that we use in our paper. You don't have to understand too much detail. The top line here is just saying that P and Q are the precondition and postcondition of the function. And we have this sort of like backward reasoning style rule that says, you know, you have to meet the precondition. And basically, what you can see this for all V thing is saying is that any value that meets the specification, you can sort of plug into the postcondition and it works intuitively. That's sort of what's going on here. So what would that look like in our proof? Well, we'd end up with this. This is sort of like morally equivalent to what you might end up with. Actually, you're going to have to use some applications of the consequence rule. You're going to have some proof obligations to discharge or whatever. But really what you're going to end up with is you're going to be allowed to assume that this array is sorted when you prove your this relation holds. Is kind of what it comes down to. But there's a problem. So maybe you spotted it, maybe not. We have freedom in the specification for implementations to do different things. So here's our sort specification. And the postcondition has some requirements on what sort outputs, but there are potentially multiple outputs that would meet this specification, right? So the implementation is free to choose among whatever different behaviors the specification allows. So to sort of concretize this a little bit, let's change our problem a little. Now, instead of just an array of integers, I'm going to have an array of these score records. So you can think of this as the score record as being a pair, a string int pair. It's a name and a score. So let's say these are test scores or something, right? And now I'm sorting the array by score and then getting the middle name out. So I've updated the postcondition just a little bit here to say that it's, you know, it's the same postcondition we had before, but we have this dot score just because we're now sorting by the score. Okay, so what is the issue here? So let's say we have as input some names and scores. Okay, so here's just a list of 5 names along with 5 scores. Note that here Leon and Rachel have the same score, right? And they're the same score sort of in the middle of the list. So this might be problems. So one thing sort could do that meets its specification is return this list where we have the ultimate median will be Rachel. So that's what will get returned from our function, right? It can also do this where it changes the order of Rachel and Leon, right? This still meets the specification because there's still it still is strictly increasing order of scores in the list, right? Or an increasing order of scores in the list. So it still meets the spec, but we have a different result now. We're returning Leon out of the list instead. A way to classify the difference here is we could say sort 1 is the stable version of the sort 2 is unstable. So remember, stable means that any keys that have the same value in the original list will appear in the same order in the sorted list. So since Leon appears first here, Leon appears first here, that makes this sort unstable. But both of these obey the specification. So what's going on here? Well, I guess you could say our refactoring was invalid because it turns out, remember our first, what we started with was a piece of code doing insertion sort, which is a stable sort. So the only thing it could ever possibly return is Rachel. But when we refactored and we replaced sort with a specification, it turns out the specification allowed enough behaviors that we could get another value here, Leon, which we introduced a new behavior to the program sort of by accident. So I guess there are multiple ways to frame what happened here. Maybe you don't care about introducing this new behavior or whatever, but an easy fix is we can add a stability condition to the specification of sort and whatever, it works. But the bigger point here is that we have specifications that allow degrees of freedom to the implementers. And even though this might cause problems in our reasoning, our formal reasoning, I want to be clear that it's good that we can do this with specifications. I mean, if our specifications only ever allowed one behavior, then that's not, doesn't give enough freedom to implementers. You could start having philosophical arguments with, if it only allows one behavior, is that not actually just an implementation or whatever? So it's important that we have these specifications, these degrees of freedom in the specifications, but we just have to make sure that we account for it in our program logics when we're reasoning about these relational properties, especially. And that's sort of what this work is about, is accounting for this freedom in a way that makes sense. So one insight that's important here is that freedom in the specification really just looks like non-determinism from the perspective of the client. So when this is a graph of the execution state space or whatever of the code that we just looked at. So we're coming into the program, we're calling sort. And from the perspective of the client, there is now some non-deterministic choice that's happening from that the implementation is going to make. Is it going to do the stable version of the sort? Is it going to do the unstable version of the sort? There's this non-deterministic branching point, and then we're going to get different, we continue through the state transitions and we get different results at the end, depending on what the implementation did. And in the general case, we're going to have, when we're doing this relational reasoning, we're going to have multiple programs. They're going to have these non-deterministic branches, and we're going to have properties we care about where we make sure all of the starting states fall within some relational precondition. So that's phi here. But maybe we care about the end states. Some of them fall within this post condition. Some of the, sometimes we care that all of the end states fall in the post condition. Sometimes we don't care about that only some of them maybe do. So to concretize this a little bit, here's a relational property that has this form, where we care that some of the end states end up in this post condition. So in one program we care that all of them do, and in one program we care that maybe only some of them do. This is actually the original motivation of why we started working on this in the first place, but we want to talk about refinement, program refinement. So what is refinement? It's when the possible behaviors of one program is a subset of the possible behaviors of another program. So if you think about our refactoring example, we could ask if our refactoring was a refinement of the original program. And in order to be a refinement, the intuition is you have to not add any new behaviors, right? So you can take away behaviors, but you can't add new behaviors. And the answer is no, because we did add a new behavior, right? In that example, we were using equality of the outputs. If you want to make sure that the two programs have the exact same set of behaviors, you can just do refinement in both directions. So refinement's maybe you could say the more general thing here. So what does this look like when we're reasoning formally about these refinement properties? Well, we want to say that any state that P1 can evaluate to, P2 can also evaluate to. So this is just another way of saying the evaluation relation of P1 is a subset of that of P2. Right? So when we're actually verifying this, you can note here that P2 can have other things that it can evaluate sigma to other things that P1 doesn't, right? That's okay, this still holds. So here we have this notion like P1, we care about all the things that P1 will evaluate to, but we only care that when we're talking about P2, we only care that certain evaluations exist, right? So this is the diagram that we had up before, where this refinement property is sort of this mix of this, these two different kinds of properties. One where we care about the, every evaluation of P1 falls within some post condition, but with P2, we only care that there exist certain evaluations there can be other evaluations too that doesn't matter to verifying our property. And really, it's just these two, the difference between these two kinds of properties is we call it the first kind safety, the first kind liveness. So safety property says that all the states we reach have to be good or whatever, have to fall within our post condition. And liveness says that for all of the preconditioned states that we have, some good state must be reachable. So we must be able to reach some state. For deterministic programs, when we're talking about just the end states, so if we were talking about just the end states of a deterministic program, these two notions sort of collapse into the same thing because you can only get to one end state. So if you're saying, well, all the end states meet a postcondition versus there exists some end state that meets a postcondition, it's the same notion if there's no non-determinism. So this only becomes interesting when things start branching out. Modulo the totality, as I've written here. So there is a difference, you know, if you're saying safety property, if you have a program that loops forever and never returns anything, you can say it vacuously meets the safety property. If we want to, if the idea of liveness is that some good state is definitely possible, then we can't do that anymore. We have to have a total logic, a total Hoare logic, and say that, you know, that actually does terminate in some good state. So modulo that concern, though, these two notions become the same in deterministic programs. Okay, so we have this this relational property where we have a mix of safety and liveness properties that we care about. We want to reason about these formally. Before we do that, though, we are going to need to find a way to specify functions in a way that lets us understand what these functions are guaranteed to be able to return instead of just a safety property on what they do return. So what do I mean by this? We need a way to specify that certain outputs of our function are possible. So to see why this is an issue, consider just a simple rand function. So the idea here is that rand will return a random number between 0 and whatever bound you give it. So here I gave it 10, it will return us a random number between 0 and 10. So here's how we might want to frame its specification. We say a precondition true, we can call rand from any program state. Postcondition is that the return value is going to be between 0 and n, right? But as we normally interpret these pre and post conditions, we interpret these in an over approximate way, usually. So what do I mean by that? It means, I just mean that any return value has to meet this post condition. But this is clearly not what we want for rand here, right? So here's an example of an implementation of rand that always returns 0, and it meets the spec in an over, excuse me, in an over approximate way. So any return value of rand that can only return one thing, 0, is going to be between 0 and n. So this works, right? But it's not the specification we want for rand. When we do, when we have this this picture here, if you look at P2 on the right, maybe at this bottom branch here, maybe this this dot in the blue circle is something that we could only get to when rand was 5 or whatever, right? And the specification doesn't tell us that 5 is definitely possible. It only tells us that any return value will fall within this post condition. So that's not good enough when we're talking about these liveness properties. We need some guarantees about what these functions can return. So there are a few different strategies for a few different ways you can sort of formalize the specification of this. I'm going to talk about template variables, which is what the tooling that we've written that uses this logic, that's how it represents these specifications. The formalization in our paper uses something slightly different, but I'm going to say roughly equivalent. But I think template variables are a nice, I think they're a good way to understand. So you can think of a template variable as a special kind of variable that appear in the specification. So it's a specification variable that says and any instantiation of this variable must be possible. Must be something that the function can actually return, or like whatever state that template variable represents must be a state that can come out of the function. So I think maybe just an example here will be clear. So we have our rand function before, but instead of specification that we had before, we're going to define some template variable. So you can define any number, but here we only need one. We're going to call it R. And as a precondition, we're going to say that R falls within this bound between 0 and n. And as a postcondition, now we're going to say x equals R. And what the specification is saying is that any R that meets this precondition is a possible return value from Rand. So hopefully this makes sense. This template variable is just a mechanism for expressing what return values must necessarily be possible in order for a function to meet this specification. So now when we do this reasoning, we can sort of like look at these branches and say, yes, all these branches in P2, when we're talking about a liveness property, and we have this existential specification, all these branches are possible. So we know that we can get to any of these states. So I actually had to, I think maybe it fell out of my slides somehow, but I had the rule, we have a rule, maybe it's coming up and I've forgotten, but we have a rule that for single execution that sort of uses these specifications in order to prove liveness properties. I actually think maybe it is coming later, so we'll maybe get to that in a second. But another key insight here is that when we're doing verification for these liveness properties, and we want to sort of do this horror style, step forward through the program, look at state transitions. We don't want to start examining these branches of these non-deterministic branches that are going to end in states that don't meet our postcondition. We want to sort of prune these away. And when we prune these away, we can sort of collapse things down to this nice deterministic looking thing that is amenable to normal like horror style reasoning. So what does it mean to prune away non-deterministic execution branches? Really, in this case, when we're expressing the specification using these template variables, pruning these execution branches just means fixing the values of these template variables to values that like work for our verification. So we have this, this stuff we want to prove. We're just going to say, okay, fix the these non-deterministic choices or whatever to things that are going to eventually work. And now this sort of just looks like the right-hand side where we've stepped into something where everything meets the postcondition, and we can continue doing like normal horror-style reasoning out of this postcondition. So the game sort of becomes here picking values of the template variables that are going to work eventually, right? And so from a standpoint of verification, that's going to sort of be the game, is that we need to resolve the non-determinism in ways that are going to make the liveness are going to work, that are going to make the executions in this existential like liveness P2 zone that are going to make them land in states that meet the postcondition. Okay, here's the rule. So it's not important to understand the nitty-gritty of this right now, but sort of above the line, we're just saying that P and Q are specifications. Again, this is sort of in the context of a single execution. The P and Q are the pre and post condition of the function. We have a few lines on this on the precondition at the bottom here. So the first one basically just says the precondition is met. The second line you can read as saying that there does exist some valid instantiation of the post condition. So it's not just like loop forever, like false or whatever. It does have to actually there does have to exist some valid instantiation of it. And like I said in the paper, our formalism is a little different for this. We don't use template variables much, but you can think of these square bracket sections as being different instantiations of the template variables, roughly. And the third line here says that, okay, we can pick some, remember our over approximate rule says anything that you pick for the spec has to work. This one says, well, you can pick one of these choices, essentially you can pick one of these template variable values that make the post condition work. And then you can sort of ignore the rest. So that's sort of what's going on with this rule. Again, this is in the context of a single execution. It's not relational. So how do we make it relational? We have this view, we have this this refinement property that we sort of have a safety. It's sort of this combination of safety and liveness property where we want to show for all executions of the program that we modified or whatever, there's exists an execution of the original program that does the same thing. So we haven't added any other behaviors. It's sort of this relational mix of over and under approximation, or safety and liveness. So how do we glue these two things together? That's what really is. It's a relational program logic that does this style of reasoning when we have functions with these specifications that are sort of like a mix of this universal safety style specification and this existential liveness style. So what does a really assertion triple, whatever it look like, quadruple, I guess, tuple, it looks like this. So here we have some relational precondition at the beginning. And we're using square brackets here because instead of curly braces, because there's some notion of totality in the liveness properties, right? So that's why we have that notation. But so in those square brackets at the beginning, we have this relational precondition. We have these alphas, which are sort of these universally quantified programs. So think of P1 in our diagram before, where it's like we're going to consider every execution of these programs. We have this tilde with a subscript E, existential quantifier. That's just a delimiter between the universals and the existentials. And then we have these etas, which are the existentially quantified programs. So this is like the P2 in the diagram before. These are the programs where we care that there exists at least one execution that does something. And then at the end, we have the psi, which is the relational postcondition. So what does this triple mean? Intuitively, it's saying for any collection of states that meets the phi, for all executions of all these alphas, there exist executions of all these etas, such that the end states of all of these things together meet the relational postcondition psi. Our notion of refinement from before is sort of like a special case of this. So in order to see that, remember this was our the way that we had refinement defined before. I'm going to sort of rewrite it with extra sigmas and just assert that some of the sigmas are equal. So now instead of just sigma, sigma prime being the beginning and ending state, we have sigma, sigma prime, and we also have the sigma 2 and sigma 2 prime. And sigma 1 is, the sigma 1s are going to be the execution state, the beginning and end state for P1. The sigma 2s are going to be the beginning and end state for P2. And this is saying that there's going to exist, the important bit here is this exists sigma 2 prime. You know, whenever we have this evaluation, there exists some end state for P2 that meets, that's equal to the state for sigma 1. So this is just a rewriting of this with extra sigmas. But we can take this sigma 1 equals sigma 2, sigma 1 prime equals sigma 2 prime, take those out, and just turn them into general relational pre and post conditions. And this is essentially the semantics of the really triple. You know, instead of being confined to just quality in the states, we can have any relational pre and post condition on the states. So here's what it looks like when we write refinement as a really triple. We're saying that, you know, if the inputs are equal, we have P1 on the left, P2 on the right. So we're executing P1 in this universal mode and P2 in this existential mode. So for all executions of P1, there exists execution of P2 such that the outputs are equal. So again, this is our notion of refinement. Refinement was originally our motivation, like I said, for looking at this, but you can express all sorts of properties in the same sort of way. So here's non-interference. If you're not familiar with what this is, you know, that's fine. But if you are, basically what's going on here is we have high state and low state. Here L represents low states. Low states are things that aren't secret, they're public knowledge. And high states are things that are secret. We don't want to leak the values of high states. So we want to make sure that for any starting states where we have the same public information, when we execute these, when we execute one program, there always exists the execution of the other program where the low states are again equal at the end. So the end states are equal, the low states are equal at the beginning, low states are equal at the end. This guarantees that we haven't actually accidentally leaked anything indirectly about the high states. Again, this is maybe more interesting if you're familiar with this type of property, but it's easy to express in really. In fact, we can also express a modified notion of this, of non-interference called limited release, where maybe we are okay with leaking certain things about the high states. So in this property, we have this H1 mod 2 equals H2 mod 2. So this is saying that the program here is allowed to leak the lowest significant bit of H1. It's allowed to leak the parity of H1, but nothing else about H1. so this is, again, it's easy to express this and really, I'm noticing these P's have like subscripts on them. They're the same program, really. It's you can imagine it's just P and P without the subscript 1, subscript 2. Anyway, again, if you're interested in these types of properties, they're actually pretty nice to express in, really. Okay, so we have this this way a way to do this specification of functions, both in an over approximate and in an under approximate way. We have this, we have ways to reason about those specifications, and then now we have this relational logic that lets us glue things together and express these properties. We have a logic for actually reasoning about these properties, which I'm not going to present here. If you want to know the details of it, I can give you pointers to the paper. But suffice it to say, there are these the same style of relational rule that that we looked at the beginning when we were sort of stepping through the relational proof. There are rules to handle the existential specifications by using that existential spec rule that we looked at. Again, I can, if anyone's interested in more details, we can pull up the paper and look at it. But we want to move on now to actually verifying these properties. So how do we do verification? Well, there are a couple different strategies. So the first one I'll talk about is RHLE. So this is our implementation in Haskell of basically verification condition generator that uses an SMT backend. It uses Z3 in order to validate the verification conditions that we generate. So it generates these verification conditions by using a weakest precondition predicate transform. The rules, as you saw, the rules for the specifications were already written in this sort of backwards reasoning style. So the predicate transformation here isn't anything too surprising. But we do end up, when we do this weakest precondition, remember there will be these existential quantifications in the rules. So this means the verification conditions are going to end up with existentially quantified template variables. So remember I said the game is going to be finding instantiations of these template variables that make our verification work. So here we're just leaning on the SMT solver for that. So we say, hey, Z3, here's verification conditions, are these valid? And it's up to Z3 to say, understand that yes, there is, or no, there isn't a instantiation of these existentially quantified template variables that make the verification work. So here's what input to RHLE looks like. This is a refinement example. So you tell RHLE what your programs are. So the for all is the things on the left hand side of the tilde, the exists are the things on the right hand side of the tilde. These are programs that I've defined down here. So you tell RHLE these are the programs. It can have arbitrary numbers of programs in the for all and exists bucket, but you tell them what they are. You tell them the relational pre and post condition. This bang here is a way to say, okay, it's ret, the value of ret in the original program versus the value of ret in the refinement program. You give it the specifications. So here we have a flip coin method, and we have all of our methods. Whenever we use whenever a method call appears in a for all, it needs to have an A spec, a universal spec. This is the over approximate or safety specification. Whenever a method is used in an exists program, then it also needs to have this E spec. This is the existential or liveness spec. And they're just encodings of the types of specs that we've talked about before. So it says you can call a flip coin from any program state, and anything that flip coin returns has to meet this post condition. In this case, it's just literally it's 0 or 1, flipping a coin. The existential spec, on the other hand, just from this universal spec, you could say, okay, flip coin return 0, just like our random example from before. That's a valid, that's a valid. It meets the spec, so that's good, but obviously that's not good enough when we're considering liveness properties. We need to guarantee that the 0 and the 1 are possible. So here we have, we declare a template variable n. Our precondition is that n is 0 or 1, and our postcondition is that the return value of the function equals n, and this has to be instantiable with any value of n that meets the precondition. So there has to be an execution that returns 0, and there has to be an execution that returns 1. So here are our two programs. All they do is they flip a coin. Depending on the result, they return 10 or 20. The refinement reverses the if and else branch. So it's going to do different things on different coin flips, but the overall set of behaviors is not going to be changed. It can return 10. Each program can return 10 and can return 20. So this should be a valid refinement. And it really does say that this is valid. Here's a slightly more interesting example, perhaps. This is a delimited release example that I pulled from a paper on modeling delimited release. So here we have two different we have one program called parity. This is the program. We can sort of use, we can use these square brackets to say we want different copies of the same program. So we want one copy running in for all mode and one copy running in exist mode, right? We're going to have secret state H, public state L, but we're okay with releasing the parity for H. So this is just basically the same example that we were looking at earlier. How do you encode this for really? Well, remember for secure information flow, the non-interference property, the basic thing is that the low state has to be the same at the end, and the beginning and the end. But to release this parity bit, you can just add to the precondition that these two things are equal, and this works out to represent the delimited release for reasons which maybe you see if you're familiar with limited release. If not, please just trust me that it correctly represents that. Then we have our program, and again, really does verify this as being correct. If you remove the delimited release line, then it says it's not correct because it does leak the lower order bit of H. Okay, so that's one way to do it, where we sort of generate these verification conditions by this weakest precondition transformation. Then we rely on Z3 to find the instances of the template variables. Another way that we just started playing with is to use a CGIS loop to do inductive synthesis to find assignments to these template variables that make verification work. So we've been using Sketch. The encoding is a little bit wonky just because of the way Sketch works, but I'll try to kind of hit the important points on the encoding. We have this uninterpreted function which Sketch will treat as being able to return any arbitrary element of its return type. So in this case, it can return any arbitrary bit. We encode the specifications of flip coin, and we also have to encode, so this is a downside of doing it this way. You need like a grammar for how you can generate the possible values of the template variable. So we have to say, in this case, it's just a bit, right? So it's actually not too bad. We can say like, the grammar is that you have like a random, I don't know, if you're familiar with Sketch, you probably recognize this pattern, but basically it's just saying, these are the two production rules in our grammar of how you can produce a bit value. So we can either do the actual bit or we can flip it. That's basically all this is saying. Then we have the encodings of the two programs. So you might recognize this from our first RHLE example. And then here's sort of the magic is that we have the harness that we're going to give to Sketch. This line number 64 is the important one. This is what's asking Sketch to say, find an instance of the bit, this bit template, this T template variable that makes the overall post condition work, right? So Sketch will do its CGIS magic to figure out that this needs to be assigned to not that in order to make the two results equal. So this works. I don't have a lot of complete data on like exactly what range of things this works over yet. The hard part is really the encoding, like getting the encoding right for Sketch, because the way you can encode things in Sketch, especially with these uninterpreted functions, is a little limiting for some of the examples that we have. But I think that this is this sort of CGIS approach is a valid way to do it. This abstraction refinement approach is a valid way to do it. Okay, here's some evaluation that we have for, this is, oh really, I don't have evaluation numbers for the Sketch-based approach yet. So as you can see, modulo this one example here, it tends to run pretty quickly. It gets the right answer. We have some program refinement examples, some non-interference examples, some delimited release examples, and we also have this other parameter usage example we came up with, which is basically saying, when is a parameter meaningful to a function? When is it actually like important to the way a function behaves? It's when, there exists for all executions of the program, there exists some other execution where the value of that parameter is different and then output is different. So as you can see, these are all simple examples. So the timing is pretty good, but we don't have any, giant industrial sized benchmarks that we've run it over. That would be nice to do in the future though. So quick summary of what we talked about. We have this modular approach to software implementation, which is good because we want to not think about implementation. We want to think about specifications. But when we're doing formal reasoning, the specifications are sort of become this black box, and we need to be careful about the way we handle them in our program logic, especially when there are degrees of freedom in the specifications that let implementations pick different behaviors. Okay, and when we verify these relational properties that are interesting to us, we need to consider the lower bounds on these specifications or consider what is necessarily possible in these specs. The game sort of becomes finding the non-deterministic choices that let us establish these liveness properties and thus establish these relational properties that we care about. So that's kind of where we are now with this work. Like I said, we have a paper, hopefully will be published soon, but still working on that. And at this point, I'd be happy to take, if anyone has any questions or anything else they want to talk about in more detail, I'm happy to answer questions. Any questions?
I'm curious. So developing all of this, what were the major difficulties that you stumbled upon?
In what way?
Well, was it developing the logic itself, or the fundamentals behind the logic were pretty much already out there in the literature, or was it implementing? Like, what were your major sources of difficulties here?
Yeah, so these relational logics already exist. For me, it was sort of, it's easy to think that the relational logics already give you what you need to do this type of verification. And you sort of have to realize that with this sort of non-deterministic choice in the specifications, you have to be sort of careful about how you express the specifications and how you treat them, and finding ways to express these existential specifications, these liveness specifications, in a way that like, works with the logic and is theoretically sound, and also is amenable to the tooling so that we can actually write these specifications and do real verification across them. It was sort of hard to find the sweet spot of expressing these specifications. Writing the tooling itself is mostly like engineering challenge. Once you have figured out the right way that the logic should work and the specs should work and all that kind of thing. So, does that answer your question?
How does the output of Z3, like I expect that can get in the way a lot of the times because debugging Z3 is very tricky.
Yeah. I mean, from an engineering perspective, we had a lot of trouble. I had a lot of trouble with Z3, especially with the Haskell bindings. I kept like sig faulting and whatever. And yeah, when something goes wrong in Z3, it's not always easy to figure out. But it is sort of both the SMT approach and the like sketching approach are both sort of like the synthesis of these template variables are sort of black boxes. So you have these tools that you're phrasing your questions in a way that the tools can find the instances of these variables. But if they can't find it and you think they should, what do you do at that point? So this is maybe more of an engineering concern or whatever if you're going to actually try to use these tools in practice. But when a verification fails when you think it should, trying to get to the bottom of why is an interesting problem, I guess.
Other questions?
Yeah, I have a question.
Okay.
I mistakenly turned down my video when I didn't want. Okay, so how does this approach compare with all the work that's happening on hyper properties, essentially hyper temporal logic properties?
Yeah, so there's definitely related work. For temporal logic properties, temporal logic looks at, it's like a modal logic over, it's like a model checking logic, right? So it doesn't operate directly over the syntax of the program. So that's something that we're doing differently here. There's also a lot of work right now. So Peter O'Hearn has work about like incorrectness logic, which is based off of like an older, previous work on this under approximate Hoare logic. That is related in the sense that they do think about under approximations, but they think about it in terms of, you know, when the entire it's sort of like normal Hoare logic, but it's reverse Hoare logic. So for any end state that meets the post condition, there has to exist some beginning state that that, you know, the program will execute into that end state. So this is different than what we're doing, because when you phrase it that way, there are now states in the precondition that in the incorrectness logic or reverse Hoare logic sense, like there are states that meet the precondition that you don't have to worry about at all. So like all that matters is that your precondition is broad enough to encompass all of the states that will allow you to get to all of the states in the postcondition, if that makes sense. But when we're doing this style of verification, we do care about all of the states in the precondition have to eventually meet the liveness condition or meet the safety condition. So sort of what the two logic, I mean, incorrectness logic is kind of geared towards like bug finding and you know, it makes sense that they use this reverse Hoare logic style in that sense. But when we're doing these sort of like verifying these like refinement properties or whatever, like this formulation is a closer match, I guess.
Okay, thanks. But I had a follow-up question to this.
Oh,
so
sure.
what's common in both your logic as well as the incorrectness logic is that it's essentially precondition, postcondition based, right? So these properties, relational properties you're talking about are essentially over, you know, input states, pairs of input states and pairs of output states. So have you thought about, or have you found instances where it would also make sense to essentially compare traces, or at least, you know, observable traces of the two programs, and not just look at their initial states and final states? And I think in a way, hyperproperties do go towards that route, but perhaps they are talking about infinite traces, right? What about finite traces?
Sure, yeah. So I mean, the hyperproperties definition, like from Clarkson, is very, I mean, it's just in terms of these trace sets, and, you know, it's a safety property if all of the trace sets meet the property, and it's a liveness property if you can always add new trace sets, right? And we don't consider the full trace sets, really. We, like you said, we consider the input-output relation. So is your question like, would it be helpful to, when doing verification of these like refinement relations, to consider full trace sets instead of just the input-output relation? Is that the question?
I think my question is, have you thought about this? Because when you're comparing two programs, there are all kinds of ways you can do that. And why was the particular choice to, you know, do input-output relational reasoning made? Did you ever consider doing relational reasoning about program traces, and why not? I'm just trying to understand these choices.
Mm-hmm. I mean, I would say the reason we chose input-output relations is just that the types of properties that we're looking at, that's what we care about. And that's what, you know, when we talk about a refinement property, we don't care about the route that we took to get to the end results. We just care about the output, what the output set is, right? So it's sort of like considering input-output relations is a natural thing to do for the types of properties we're considering. But, you know, there are existing tools. So there's like, you know, LTL or whatever these hyper LTL logic. Hyper LTL is like this temporal logic that reasons about hyperproperties, right? But in order to use tools like that, we would have to find a way to translate our code. Because when we want to do like the syntax-based program logic reasonings, we'd have to like translate into some like LTL formula, like temporal formula or whatever. Which you know, I haven't looked at what the mechanics of doing that translation would be like. But our goal here was to have something that operates directly over the program syntax.
Yeah. No, it does not make sense for you to look into hyper LTL and so on unless you you find an application that needs those kinds of logic.
Mhm. Yeah.
I was just curious if you had come across anything that probably does, but it looks like you haven't.
Yeah, we haven't come across anything that will do it. And I'll also say that reverse OR logic and correctness logic, these logics tend to also not be relational as well. So being able to use under approximation, a combination of over and under approximation in a relational setting is what we're going for. Yeah, and we haven't found anything else that does this. So.
Okay, thanks.
Are there any other questions, comments?
So what's next? Where do you want to take this?
So I think there are some different directions that we could go. One thing with the verification is that our verification strategy is a little simplistic right now. When we generate verification conditions, we just step backwards through the program sequentially. So this corresponds to like a program where you just concatenate all the programs together, right? And it's definitely possible, and there's existing work by like Marcelo Souza and Ishal Dillig, the Cartesian OR logic work, where they construct product programs inside the middle of these things, or step through the programs in more intelligent ways so that you can have more performant verification conditions. So I think it'd be interesting to look at that. I also think it would be interesting to look at doing synthesis of loop invariance in an existential context. It's sort of interesting because when you're doing the existential verification, you have establishing these Leibniz properties. You have the freedom to sort of throw away branches that don't work for you. Like all you're trying to do is find a path through the program that ends in some post condition. So I think this might be interesting for loop invariant synthesis because it might make the problem in some ways more tractable or whatever. Like you can start, unrolling loops and throwing branches away and whatever you need to do to get to the final state that you want. So I think that could be interesting. As far as more like how to apply this work, I think a lot of this was originally motivated by work I was trying to do with automatic API migration. So I think it would be interesting to apply RHLE to this domain of saying, I have one API that does something. I have another API that does the same things, but has different definitions or whatever. And maybe I want to synthesize some shim layer between the original API and the new API. In order to do that, I have to reason relationally like this. So like I have to say, okay, when is my shim layer that I've synthesized correct, right? I need to express that as a property. So, and it's going to be one of these like really style for all exist properties if what I care about is refinement. So sort of having really be the properties that we express, the ground truth properties we use in some sort of like CGIS loop or whatever. I think that could be an interesting work as well.
Yeah, this last one is really cool. I love it.
Thanks. Other questions?
Well, I think we can thank the speaker then. Thank you so much, Rob.
Thanks for listening to me.
All right, see everyone next Friday. We are having another invited speaker next Friday. So that will be